Alright, so back to continuing the video. Let me just get rid of what's going on here. I don't know. Back to continuing the video from before. Like I was saying, is like we're just going to compare the linear speed of the 5.5 inch blade compared to the 7.25 inch blade. We're just going to go straight to finding the linear speed. So just I'm going to walk you kind of through one of them, and then the other one is the same thing. Just you change it from 4,500 to 5,000. So let's walk through the 5.5 inch blade. You're going to go 4,500 revolutions in 1 second. And then since I'm going all the way to linear, I need to multiply that by 2 pi and then the radius to figure out exactly how far it's going around in one circumference. So we're going to multiply that by 2.25. Since that's the radius, it's half of the diameter that the blade is measured at in one revolution. So as soon as you attach the radius to this, you've now put a dimension to it. So that dimension is inches in this case. So we're sitting at, when we calculate, inches per second. And since I want the linear speed to be done in feet per second, we're going to multiply again by 12 inches on the bottom is equivalent to 1 foot, just to kind of cancel that out. And as you multiply those across, you get 5.5 here. When you take it times 2 and you take that times 4,500 and you divide by a 12, you're going to get the linear speed for that 5-inch blade. So 4,500 times 2 times pi times 2.25. And then you divide by 12 and you're going to get 5,301.44, which would be your linear speed for that 5.5 inch blade. Just checking my math here. Yep, and that'll be feet per inches. And then you do the same process. The only thing that's going to change is that 4,500 now will become 5,000. And then that, instead of 2.25, it's going to be 3.75, then would be your inches here. So like on the answer key that I shared with you guys, I made it be 7.25 pi, which gives you the distance of the speed. So that's looking at that one. To keep in mind, everything will be labeled on the test. Angular speed is just right here. It's your 2 pi over r. It's how fast the motor is moving. With the linear speed, it's because that motor is moving so fast. What is the linear speed? How fast is the tire going? So let's go ahead and look at number 3. If you're a helicopter looking down the ground, which is a 100-foot diameter cloth dartboard, lying in the ground with 36 equal wedges. So kind of just getting a picture. My ugly looking drawing there. We have 36 little wedges that are being divided into. So I'm going to kind of just not get into 36 of them, obviously, since I don't think I can draw that accurately. But we're going to kind of just think about this in a little smaller scale. So we're looking at 360 degrees is 1 revolution. I'm dividing into 36 equal pieces. So this one right now is divided into 16 equal pieces. But if I continue to break that up, I got 36 equal wedges. And if a full circle is 360 degrees, I want to know what is the degree value if we have 36 equal pieces. That means the angle that's being created from the center, your terminal side, and your initial side is going to be right there. And that angle, in this case, is going to be 10 degrees. This is your theta. So that means for every little wedge that we have 10 degrees, 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 all the way until we get to 360. And we know that this distance is going to have to be 50 feet wide. So the 2 questions I'm asking is how much area does 8 of those wedges take up on the ground? So I'm looking for the area of a sector. So 1, 2, 3, 4, 5, 6, 7, 8 of those. I want to know how much that space is taking up. So we're going to take the area. If I have 8 of those, my new angle is going to become 10 times 8, which is 80 degrees. So in my picture, this is 80 degrees that 8 sections are taking up, and I want to know the area for that. So the area formula of a sector, if we're doing it in degrees, is theta over 360 times pi r squared. Or if you're doing it in radians, it's 1/2 r squared theta. And since we're already in degrees, I'm going to kind of leave this in degrees. So we're going to go 80 over 360 times pi with the radius of 50 squared. So 80 times pi times 50 squared, it's going to, and then dividing by 360 gives you an area of 1,745.33 feet squared. So that's the area that you have a chance of landing at. Now, if I'm asking how long is the arc length, then we're talking S. So we're talking the arc length is how far is it in this image. This is the S, from 0 to 80 degrees. So similar to before, you got theta divided by 360 times 2 pi r, because you're taking part of the circumference. Or you can go S is equal to r theta in radians. So this is degrees. This one's in degrees, this was in radians. So we'll kind of draw a little divide here. So since we're in degrees, I'm going to take 80, divide by 360, and take that times 2 times pi times my radius, which is 50. And when you calculate all that out, we take 80 times 2 times pi times 50 divided by 360. You're going to get an arc length of 69.81 feet. So this is the border for that 8 wedges that there are. And this would be the area for those 8 wedges. And then from there we can get into the probability. But keep in mind, this is only for radians. It's a really nice formula, but right now, since we're doing this in degrees, this one is for radians, as well as this one right there. So if you can convert the degrees to radians, you could do it that way. Still going to get the same answer. Just keep in mind that arc length is S, area is A. And these will be some formulas that you're going to need to know or be able to at least remember or process through come your test. And the last one. San Francisco Bay is an inlet of the Pacific Ocean. At the dock, the depth of the water is 6 feet at low tide. And that's at 3 o'clock in the morning. And at the high tide is 87 feet, which occurs every 6 hours. It is currently 11 p.m. Draw a graph showing the depth of the water and write a sinoid function. So we kind of want to just get a general, oops, that's a really bad line. So let's redo that one. Delete that line. So let's draw a picture here. So we got our crosshairs. I'm going to try drawing this as straight as possible for us. And we got our middle point. So we have a high tide and we have a low tide. And at the low tide, in this case at 3 a.m., our lowest is going to be 6. And our high tide is 87. So the maximum then we want to look at is 87. And the minimum is 6. So that distance right now covers a span of 81. So we need to find that middle value that's halfway between 87 and 6. So if we take 87 plus 6 and we divide by 2, this middle ground here, which is our vertical shift in our graph, in other words, where it is when everything is constant, is at 46.5. So 46.5 is my vertical shift. So we got VS, vertical shift at 46.5. It's our wave of axis. It's where everything is at its equilibrium point, which helps us find our amplitude. So amplitude is the distance from our vertical shift all the way up to our max, or vice versa down to the minimum. So 46.5 minus 6, that's going to give us an amplitude of 40.5. So this information right here and this information right here allows us to say that this thing is fluctuating between temperatures, or between feet from the equilibrium point. So we have our axis, we have our amplitude. Now we need to think about our period. So currently it's 11 p.m. So when we are 4 hours past 11 p.m., so at 3 a.m. it's supposed to be at its lowest. So that's 4 hours beyond the current time. So this is at 11 o'clock here is my starting point. But now I'm saying at 3 a.m. we're at our minimum. So I'm going to put a dot at low, and then every 6 hours it goes from low tide to high tide and right back down. So therefore our period then is going to be 6 hours in this case. So that means I'm going to extend this line out. Let's go back to that red marker here. If I extend this line out, it's going to go back to its cycle 6 hours later. So 10 hours later, I'm going to be at my low point. And that means halfway in between, at 7, it's going to be at my maximum. And then at 5.5, it's going to be right at the equilibrium. And at 8.5 hours, or 8:30, it's going to be at my equilibrium again. So my graph, let's switch the colors here. Let's go to blue. Is going to kind of go like this. Every 6 hours, it's going to repeat. So 4 o'clock to 10 o'clock is one complete tide. 10 o'clock to 3 o'clock will be the next one, or 4 o'clock will be the next one. So this is the time after 11 p.m. So to write my sinusoid down, we got y is equal to 40.5. And I'm going to kind of go cosine with this. Cosine, since cosine starts low, I'm going to go cosine of my b value, which my b value is calculated by taking 2 pi and dividing it by my period, which is 6. So 2 pi over 3. X, I'm going to kind of wait on my shift to kind of see. But we kind of have an idea, since I'm shifting over here 4 and we're starting at the low. Where's the lowest point? It took 4 hours. So I'm going to kind of go minus 4. And then since I'm starting low instead of high, I'm going to attach a negative. It causes that reflection. So my equation is the amplitude, the B value, the vertical shift, and then of course I ran out of room. Typical Mr. Laux. We're going to add 46.5. So this would be my whole sinoid function that would represent the San Francisco Bay coming in and coming out. So when I ask the question, what is the depth at 7 o'clock at night? Well, if it's 11 p.m., how many hours is that past? You're looking at 20 hours have passed. So when I solve this on my calculator, I'm going to go negative 40.5 cosine of 2 pi over 3, 20 minus 4 plus 46.5. And we need to make sure that our calculator is in radians. So your calculator, you're going to calculate this whole cosine thing first. So let's switch colors here quick. You're going to calculate this first, multiply by negative 40.5, and add 46.5. And you're going to get 66.75. So that is the height of the wave currently at 7 p.m. at night. I hope this helped. Please review this. If you got questions, please come on in. Your test will obviously be next class. So thank you.